What up, everybody? Welcome to another episode of Ask Paul, where you can submit your questions to me via our website at www.paulabernathy.com, all part of Electrical Code Academy's network of videos, podcasts, all of the courses you need for residential wiring, commercial wiring, grounding and bonding, and our infamous Fast Tracks program, which has helped literally thousands of people pass their electrical exam. But not only that, learn the NEC to be able to retain it. That's the key. You spend the money, you don't just want to get past the test. I know that's your motivation up front, but at the end of the day, you want to be able to retain this stuff so that it helps you out in the field. And we don't get paid to do things twice. We get paid to do things once accurately. And that's what the Fast Tracks program is all about. So if you haven't heard about the Fast Tracks program, where you been? It's all the rage. It is all online. It is extensive. It has questions. It has a Wednesday night live session that I help answer your questions. And it's just so much involved in the program that, yeah, there's no way you can match it anywhere. Okay? We don't leave you hanging, I should say. We don't leave you hanging. We teach you the code, and that's what you're in it for, right? To learn the code. And then you can get to the work you need to do, all putting in the boxes and pulling the cables, all that stuff. But code is always intertwined with any of that anyway, whether we want to admit it or not, right? Okay, so back to the episode. So I had a question that was submitted to me that said, Paul, will you try to explain what code sections that I need to utilize when I'm sizing overhead service conductors, underground service conductors, or service entrance conductors, whether they're from overhead or an underground? Will you please, and we've got all these definitions in Article 100 for, again, overhead service conductors, underground service conductors, service entrance conductors overhead, service entrance conductors underground. We have all these definitions. But the question that was submitted to me was, can you show me the different sections that I need to be in when I'm sizing and determining ampacity for service conductors in general? And so we're going to go over that and kind of give you some guidance on that. But before I even get into that, I think it's important to understand that when you're doing a service conductor sizing and ampacity, all of this is based on doing a calculation. And I can tell you right now, and I've got the data to back it. If you look at calculations, and of course, again, talking about our Fast Tracks program, which is, again, the most extensive exam prep and NEC learning system out there, I am able to gather what's called analytics on specific units that are in that program that focus on these types of topics. And for example, in our Unit 8, in our Unit 11, in our Unit 13, it is very driven towards calculations, service calculations for single family, multifamily, optional, standard methods. All of that gets drummed into the student, and it still can get confusing because it's kind of a dance you have to do through the NEC. But you need to understand how to do the calculations. Now, I get it. Today, most people in the real world just look at something and say, okay, that's 200 amp, that's 400 amp, or they rely on the engineer to do the calculations and it be submitted on a blueprint. And I don't expect commercial electricians to sit down and do the entire calculation of a multifamily building or a non-residential structure. That's done by the engineer. And I have a lot of engineer followers, a lot of engineers that tune into the podcasts. So that's, one of those things that I'm saying, if the engineer already does it, I'm talking to you engineers. You need to know how to do it. And for 1 and 2 family dwellings, for even in multifamily dwellings, the individual dwelling units, it's really good for the electrician to understand the concepts of doing a calculation. And all of this is covered in Article 220 of the National Electrical Code. I also should mention, I am always using the latest edition of the National Electrical Code. From time to time, I get people that they'll say, well, that's not found in the 2017, or I can't find that in the 2011 or the 2008. That's because I'm using the 2020. I'm always going to use the most recently published edition, maybe not the most recently adopted edition in your jurisdiction, but it will be the most recently published edition of the National Electrical Code. In this case, it's the 2020 edition. So let's kind of dig into this. So when I got the kind of question, I kind of thought about it and I said, okay, I'm assuming that he or she knows how to do a load calculation. And they understand that in Article 220, you have Part 2, which is your branches, but it's also the foundation for the values that you're going to need to use in Part 3, which is a standard method calculation. And then, of course, you have an optional method in Part 4, which gives you its own direction within Part 4. So it's obviously much easier than it is in Part 3. There's so many working pieces in Part 3. And I always thought that the student should know that, for example, when I'm doing a calculation, there is what's called a connected load and there's a calculated load. And the connected load is simply taking face value of the loads before you apply any demands to that. And then, of course, the calculated load would be the resulting value after you apply some type of demand to that or some type of calculation, whether it's adjustment or correction or whatnot. You'll have a resulting calculated load. So when it comes to things like ungrounded hot conductors, you're going to use either Part 3 or Part 4 ultimately after you put all the pieces together that are in Part 2 or individually directed in Part 4 for optional method. At the end of the day, you come up with a VA value, that's volt amperes, and you're going to divide that by 240 volts if that's what you're dealing with, or 360 if it's 208. Well, those type of concepts, right? Or 831 if it's 480. So you've got these, again, dealing with three phase, it's the square root of 3, right? You've got all these things, but when it comes to the grounded conductor, in many cases will be a neutral, but grounded conductor is always the case when it's a grounded system, but a neutral is what we probably would talk about the most when it comes to single family dwellings, multifamily dwellings, things like that. 120, 240 volts, grounded loads. You can also have 120, 208, grounded systems. When you're sizing the grounded neutral, in that case, you have to size it based on Part 3 of Article 220, because the method to do this is not over in Part 4 for the optional method. It is in Part 3. So you're kind of locked in 220.61 in all of the allowances for sizing and all that for the neutral. Now, keep in mind that you have to size the neutral, and we're going to look at that today. You still got to size the ungrounded hot conductors to handle the calculated load based on a calculation. And that goes the same for the grounded neutral. It still has to be sized based on a calculated neutral load. But there are going to be rules in the code which say, look, I know that you're going to size this grounded conductor at based on the calculated load, but there's certain rules that say, yeah, but you still can't have a grounded conductor smaller than this size. And so we're going to be looking at that as well today on all those different topics that we'll be covering. Okay. All right. So let's kind of get started. So we're going to go to Part 2 of Article 230, which is titled Overhead Service Conductors. We're going to start there dealing with those conductors. And we're going to look at 230.23, and it's titled Size and Ampacity. Can't get any easier than that, right? And it's broken down into an A, B, and C. A being your general rules that you have to follow. B being the minimum size requirement in the code. Could be larger, but this is a minimum size restriction here. And then, of course, C is going to give us direction on sizing that grounded conductor. Okay? So let's look at the general first. 230.23a, it says, conductors shall have a sufficient ampacity to carry the current for the load as calculated in accordance with Article 220 and shall have adequate mechanical strength. Of course, these are overhead service conductors, so they are from an overhead supply. So, obviously mechanical strength, how they're supported on messenger or whatnot, that type of thing. But when it comes to, again, sufficient ampacity, it gives us that direction to Article 220. So you have to do a calculation. Whether you're doing the standard method or the optional method, you still have to do a calculation. Okay. Now it goes on to B. It says, okay, overhead service conductors, a minimum size. It says the conductors shall not be smaller than 8 AWG copper or 6 AWG aluminum or copper-clad aluminum. Remembering that copper-clad aluminum is really aluminum with a copper veneer, if you will. It's metallurgically bonded copper to aluminum. But it's, as far as ampacity goes, it's still aluminum. So keeping that in mind. So that's your gist. So our service conductors that are overhead service conductors, a minimum size, 8 copper, 6 aluminum. Now, there is an exception. This is, for example, if you had a separate water heater, let's say, on your structure, and you had a different, I guess, net rating or charge rating or power rating, maybe a lower price schedule, then one of the allowances to bring additional services to a building might be for that. And if that's the case, then you might have a conductor, ungrounded conductor that would be smaller. And that's kind of what it covers in here. The caveat to this is that these conductors are only limited loads from a single branch circuit, such as maybe a small polyphase motor or a controlled water heater, something like that. Then you do have the allowance for conductors that could be smaller when it comes to the ungrounded hot, if you will. But the general rule here is, in our case, we're just talking overhead service conductors. So we're going to say they can't be smaller than an 8 and copper, and can be smaller than a 6 aluminum. Okay. Now, that's our ungrounded. Now, chances with the calculated loads are going to be larger than that anyway, but that's just kind of gives you some direction. Now, when it comes to the grounded conductor, because we're going to size those ungrounded, the hots, based on part 3 or part 4 of Article 220, we're also going to size the grounded conductor as part of part 3, not part 4. Part 3, because 220.61 appears in part 3, which is dealing with the grounded neutral conductor sizing, it's not over in part 4. It's in part 3. So even if I choose to use the optional method for my load calc under Article 220, under part 4, I'm still going to have to do at least a standard method for all of those given 120 volt loads, like the 3 VA per square foot, a minimum of 2 small appliance branch circuits, which all of those are going to be 120 loads anyway. So that's why you do it. All of the appliances that happen to be 120 volts, all those type of things. And of course, ranges, I can take its value at 70%, dryers, same thing, all those type of things. But that's covered under part 3, not under part 4. So just remember that when you're doing your calculations and in the field, you're probably going to do part 4 optional method most all the time. When it comes to the grounded neutral conductor, then you're going to have to be sizing under part 3. So you're not going to totally get to ignore using part 3, even if you're so heavily in part 4 for optional methods. Still got to know how to do it, right? And if you don't know how to do it, we have videos on that over on our YouTube channel. Just go to youtube.com/master the NEC. Go to the playlist called Calculations, and in there you will see videos on how to do service calculations for single family, multifamily. They're all there. Just go check them out. All right, so it goes on to say now, let's size. What do we do for sizing that grounded conductor? It says, under 230.23C, and again, we're talking overhead service conductors, it says the grounded conductor shall not be less than the minimum size as required by 250.24C. Okay, so in 250.24C, that's talking about the grounded conductor brought to service equipment. Now, we're not talking about a need for a neutral downstream of your service equipment. That is purely optional depending on what your loads are. Maybe you have loads that don't need a neutral. Okay, maybe you have a panel that's designed to handle this situation and there is no neutral loads in it. It's only handling face-to-face types of loads. There's allowances downstream, but when it comes to the service, you have to bring a grounded conductor to the service. Okay, so if you look at C, we're going to focus on C1 and C2 just because of where they send you as far as their reference. Because again, it told us that the grounded conductor cannot be smaller than what's given in 250.24C. So it can't be less than the minimum size here. So when you get here, you're going to notice real quickly in C1 and C2, it doesn't give you any sizes. Now, it does tell you in C2 when it comes to parallels that it can't be smaller than 1/0. Okay, so that's a given, something you should remember, especially if you're preparing for an exam. You never have parallel conductors in general use that are going to be paralleled smaller than a 1/0. But it sends you somewhere important. So C1 says sizing for a single raceway or cable. Again, we're sizing the grounded conductor. It says the grounded conductor shall not be smaller than specified in table 250.102C1. Now, before people get confused, you still have to remember the general principles here. You have to size the grounded conductor to handle the calculated load for that grounded conductor. Okay, you've got to size it. What this is saying is that it cannot be smaller than what's given in 250.102C1. Okay, you with me? So if my calculated grounded conductor load was less than the minimum size conductor that's required in 250.102C1, then I'd have a problem. I couldn't size it based on the calculated load. It can't be less than what's given in table 250.102C1. Now, what's most of the time going to happen is it's always going to be larger than what's in this table because that's the minimum size it can't be smaller than. Usually, it would be larger, but understanding that the grounded neutral conductor handles the imbalanced load, so it could be smaller, but you just need to remember in no case can it be smaller than what's going to be referenced in 250.102C1, but it could be larger based on the calculated load of that grounded neutral conductor. You with me? Hopefully that makes all sense. If it doesn't, pause it, go back and listen again so that you can get the concept. All right. So 250.102C1, if we take a quick look at that, you'll see that table. That table is based on, you see the header, it says grounded conductor. So one of the things that I usually tell people at this stage, I says, okay, you can go look at 250.102C1, the code reference, and it's going to pretty much say the same as what we saw back in 250.24. So it sends you to the table. If, for example, our service did a calculation and the conductors were 4/0, which typically 4/0 aluminum for 200 amp service or 2/0 copper, let's say it's 2/0 copper. So then you would go to this table and you say, okay, what is the minimum size that I can't go smaller than for the grounded conductor? And you'll notice that this table says size of the largest ungrounded conductor. So you have to do your load calc. You have to determine what your ungrounded hot conductor sizes are. Once you establish that, then you're going to go over here and say, okay, well, copper column to the left, 2/0 or 3/0. So I'm in 2/0. I go to the right and notice that it says a 4. So it says in the title of those two columns, it says size of the grounded conductor or bonding jumper. So we're talking about the minimum size that we can't be smaller than for the grounded conductor. And this says a 4 copper or a 2 aluminum. So it can't be smaller than that. Now, if our calculated load for our neutral is less than it would be, comes up with a conductor that would size based on whatever the calculated load, you come up with the VA and you divide that by the voltage. If it ends up being a conductor selection that would be smaller than a 2, then you could not do that. You'd have to go to the 2. Because it can't be smaller than the 2. Now, if your calculated load is much larger than what would be needed for a 2, then that's okay. You're going to size that grounded conductor based on the calculated load. You with me? I am a bit redundant here, but I want to make sure that I hammer this home and that you understand it. I have every now and then somebody will post a negative thing about my redundancy. If you don't like it, don't listen to my podcast. That's simple. Just don't listen. If you don't like what I'm giving you, don't listen. God, I can't make it any simpler than that, right? But if you get something out of it, you're welcome. All right, so there you go. And 2/0 is going to need a 4. All right, so let's kind of go back now. So in this case, we would have to do, if we're doing overhead service conductors, I'm back at part 2 at 230.23. I have to do a load calc. And I have to come up with that load calculation, whether I'm using the standard method or optional method. and I size my conductors accordingly. Once I know those conductor sizes, then when I'm sizing my grounded conductor, I first want to go to 250.24C, which is ultimately going to send me to 250.102C1, the table. Use those ungrounded conductors that we calculated using, again, standard or optional method, your flavor. And go down and see what is the minimum size of my grounded conductor that it can't be smaller than. And you write that down. Then you go back and say, okay, now I have to do a load calculation under the standard method for my grounded conductor. And then whatever size results from the VA based on my calculation, and then you divide that by the 240 volts or whatever you're dealing with. Then you say, okay, here's my ampacity. Then you go to table 31016, and for example, and you size the conductor you need under the 75-degree column. And then you go, okay, is this conductor equal to or greater than the size that it couldn't be less than in table 250.102C1? And if it's larger than that or equal to that, then you're good to go. And that's how you would size your grounded conductor. Okay, so that's overhead service conductors. All right, now let's move on to the next scenario. So that's overhead. So when we're talking about underground service conductors, and hopefully I'm answering the questions for the submitter, and if not, you can always reply and let me know a little more details necessary. So the next one is talking about, okay, how do we size the conductors if it's an underground service conductors? All right, in this one, you're in part 3, still in Article 230, but where we're going to go down is to 230.31. And you'll notice that it also says size and ampacity. And you have your general again, you have your minimum size, and we have grounded again. And again, it's going to be the same exact concepts, so we won't rehash this out. It's going to tell you that the ungrounded service conductors shall have sufficient ampacity to carry the current for the load as calculated in accordance with Article 220. Same concept, mechanical strength, yada, yada. Okay. Same concept. The minimum size, same thing here, 8 copper, 6 aluminum, or 6 copper clad aluminum. And then, of course, the neutral is going to send you to 250.24C, which ultimately is going to send you to table 250.102C1 for the minimum size. Also knowing that we still have to do a load calculation, and the grounded conductor has to be sized to handle the calculated load, but again, can't be smaller than table 250.102C1. And I've said that again, and it should be crystal clear at this point. All right, so the next thing we would want to look at is, I guess it's part 4, which now we're going to be talking about service entrance conductors. And to get a full understanding of how they differ from underground service conductors versus overhead service conductors, you really need to go look at the definitions, because again, the definition is going to make it really clear, because we're not talking about service laterals. We're not talking about service drops here. Okay. They're outside of the scope of the NEC. Okay. We're talking about what is under the scope of the NEC. And that is underground service conductors, overhead service conductors, and of course, the transition from the service point or the point of attachment on the building, what runs down the side of your building, say down to your meter, they would be service entrance conductors. Okay. So understanding the nuances, if I had a pole on my property and the utility stopped at the pole, and then I controlled the overhead conductors that go down to the side of my building, which can happen on large rural properties, then those would be overhead service conductors. And then once they got to the point of attachment of the building, they would change over to service entrance conductors. Okay. So again, and they would be service entrance conductors either overhead, or if they were coming underground, let's say you had a transformer pad on your property, and that's where the utility stopped and the line of demarcation, and now you're responsible as an electrician for running those conductors underground to the meter, let's say, then that would be underground service conductors, or depending on how they're run, they could just be underground service entrance conductors. Again, go read the definitions. It's kind of hard for me to show that here in a podcast because that's a visual thing. But again, we're talking about what the electrician has control over, not what we don't have control over. All right, so for service entrance conductors, most people understand that when I say service entrance conductors, it also is going to cover SE cables those type of scenarios where you have SCR, SCU, and again, USE-2 could be utilized, USE could be utilized again as service entrance conductors. So again, go back and follow that Article 100 and you can see all the definitions and you won't have any problem. All right, so now when we're talking about service entrance conductors, we would look at 230.42, and this would be minimum sizing and ampacity. Now, in this case here, it says General A, says service entrance conductors shall have an ampacity of not less than the maximum load to be served. Okay, so they have to be sized to handle the maximum load to be served in their application. Now, once we establish that we have service entrance conductors, then it gets a little bit more complicated for these conductors. So when sizing, you need to make sure that you truly understand, okay, truly understand the steps here, which are going to be different than what we've looked at in part 2 and part 3. When we're dealing in part 4, if you define what you're dealing with as service entrance conductors, then we have to look at something different here. And it says, service entrance conductors shall have an ampacity, again, not less than the maximum load to be served. So you do a calculation, whatever that calculation is, that is the load to be served, and you make sure you size your conductors accordingly. Now, it goes on a little further. It says, conductors shall be sized not less than the larger or the largest of 230.42A1 or A2. Now it says load shall be determined in accordance with part 3, part 4, and part 5 of Article 220. Now we've rehashed this. We know that, again, the same concepts apply here. But it's so important to know when you're dealing with service entrance conductors versus overhead or underground service conductors. We're dealing with service entrance conductors. Again, go read the definition. And so we have to size it based on the larger of A1 versus A2 of 230.42. So it also goes on to says the ampacity shall be determined from 310.14, which is going to also, remember that we are going to do it and we are okay to use the insulation, say a 90-degree insulation for adjustment and correction purposes, as long as we don't exceed the values for the terminal limitations in 110.14C. Okay. So it says the maximum current of busways shall be the value for which the busway has been listed or labeled. Obviously, if it's 200 amp busway, 1000 amp busway, you're not going to exceed what the busway is rated for. Like that's one of those ones where you go. All right. So what does A1 have to do here? And again, we're in 230.42A. And A1 says, okay, look, where the service entrance conductors are supplied, that supply continuous loads or a combination of non-continuous and continuous loads, the minimum service entrance conductor size shall have an ampacity not less than the sum of the non-continuous loads. So that's just face value of what your non-continuous loads are that you calculate out, plus 125% of the continuous loads. Okay, so now A1, there's certain things to remember here. You're going to be in A1 for your conductor sizing first, because you got to have something to compare it to A2, right? If you have continuous loads involved. Probably not what you're going to have in a 1 and 2 family dwelling. Okay, probably not going to have it. Now, you might in a multifamily dwelling because you have common areas, and that's going to be different, but probably not in the individual dwelling units. So, and again, those typically are going to be feeders, so it doesn't come into play here. Not always, but in our case, we would say they were feeders and not going to come into play. So if I've got continuous loads, or I've got continuous loads and non-continuous load, this gives me some direction on how to size the conductors. So I have to size the conductors to at least handle 125% of whatever my continuous load is. And that are loads that are on for 3 hours or more at their maximum value. Okay, if they're not at their maximum value, they're not a continuous load. Or if somewhere else in the code tells me to take something as a continuous load. And then I will take that value, that whatever that load value is, at a continuous load because it's part of a calculation. And they're telling me to do it. So if that's the case, I'm going to be in A1. Now, people ask me all the time, what if I have no continuous loads at all? Okay, if you have no continuous loads, then you're going to ignore A1 and you're going to look at A2. So A2 is saying, okay, look, what is A2? And there are some exceptions to A1, but we're just going to kind of keep it simple because it's not really a lesson. I'm trying to answer the code question. A2 says the minimum service entrance conductor size shall have an ampacity not less than the maximum load to be served after the application of any adjustment or correction. So this might be where you have the current carrying conductors that exceed 3, so 4 or more. Or this might be where your conductors are installed in a location with an elevated ambient temperature that's higher than 30 degrees Celsius and 86 degrees Fahrenheit. So you're going to have to change, by doing a calculation, the ampacity of that conductor because of a condition of use. So after that condition of use is applied, I need to make sure that I still have a conductor that can handle what? My calculated load after the application of the adjustment and corrections. So once I determine that, then I size my conductor accordingly. And if I did have continuous loads, then and I sized my first conductor and I came up with a certain size. And then if I had like adjustment and corrections, then I got to compare that to A2. And whatever that conductor resulted in, I now have to compare the two. And whichever results in the larger conductor, that's the one I'm going to go with. If there's no continuous loads involved in it, then you skip A1, you go straight to A2. Okay. Now, ironically, as somebody said to me, Paul, what if I have no continuous loads and I have no conditions of use, no adjustment or corrections are involved? Then you know what? Then you simply size your conductor based on your calculated load, and that's it. And of course, you're going to go to your terminal limitations. If no other information is given, then you're going to go, if it's over 100 amps or more, you're going to go to 75 degree column. If it's less than 100 amps, you're going to go to the 60 degree column. Pretty straightforward, right? Okay. So this is where you need to be, but we're not done yet. Okay. We're just kind of wrapping this all up, but that's kind of another article, or excuse me, another section that the individual needs to look at. So far we've looked at, where are we at here? Let's see. We've looked at section 230.24 for the overhead service conductors. We've looked at 230.31, which is under part 3 for the underground service conductors. We've looked at part 4 under section 230.42. That's for service entrance conductors. And we determined whether or not you have continuous loads and non-continuous loads, or you have the conductors that have to be sized based on handling the load after adjustment and corrections. And I also got a couple other little tips that I'll remind you about this when it comes to these conductor sizes using A1 or A2. When you are doing A1, you don't consider the adjustment or corrections if they're present. You just take them continuous loads at 125 and size your conductor. And if you have continuous loads plus non-continuous, then again, you add the two together, the 125% of the continuous and 100% of the non, and select your conductor. Okay. And you go straight to the 75 degree column if your values are over 100 amperes. If you're under 100 amperes, you go to 60. Okay. That is nothing to do with conditions of use in that one. You're simply sizing it first if you have continuous loads at 125%. And if you also have a non-continuous loads, you take them at 100%. Again, I'm redundant, but I want to make it clear. When you're using C2 to compare to C1, you're not going to take the loads as a continuous load. You're going to take the load as its face value. See, there's a key difference because that is the load. So even when we do something as a continuous load, that doesn't change what the actual load is. The load is the load. For example, if I have something that somebody says that I have 20 amps of continuous load, okay, well, that if the code tells me it's 20 amps continuous load, then I take it as 20 amps continuous load. If I have something that is 16 amperes and I tell you that it's continuous load, then it would be 16 times 1.25, which is 20 amperes, and you size your conductors for that continuous load. However, the actual load is still just 16 amps. So when you're using A2, and this goes the same for when you're doing branch circuit sizing, same with the feeders, You simply take it at its actual load, right? The actual load. Even though we're applying 125% to it for a continuous load, if that's what's present, that doesn't change what the actual load is. It's just an effort or an exercise that we do. So remember the two and the difference. A1, no conditions of use. A2, you don't worry about continuous loads. You apply the conditions of use. And size the conductor, and whichever results in the larger conductor, that's what you go with. Okay, kind of a long explanation, but again, I think that it's one of the most important aspects of the code to make sure that people understand it. All right, now, so we've done this sizing. One of the other important aspects that we really have to look at is now we have to understand what overcurrent protection is. And the overcurrent protection of our ungrounded conductors. So we sized them. We know what they are. We sized the grounded conductor. We sized the ungrounded conductors. Now we have overcurrent protection. Now, obviously, the overcurrent protection is on our ungrounded conductors. Okay. So the next thing that I would steer you to is you need to be looking, and in this case, it's going to be section 230.90. And as far as the parts you're looking at, let's see here, that's going to be 4, bear with me, because I'm bad on Roman numerals. 4, 5, 6. Looks like part 7. So you'll be in part 7, which is titled Service Equipment and Overcurrent Protection. And it says ungrounded conductors. Now, well, first, 230.90 says where required. It says each ungrounded service conductor shall have overload protection. Okay. Now, 230.90A says ungrounded conductors. It says such protection shall be provided by an overcurrent device in series with each ungrounded conductor and has a rating or setting not higher than the ampacity of the conductor. Okay. So you've sized your conductor. You're sizing everything based on your loads that you had, your calculated loads, and your overcurrent protection rating is not higher than the ampacity of your conductor. Now, we have some exceptions, and I'll explain those which are more relevant to our situation, but the general rule is that whatever my ampacity of my conductor is, that my overcurrent protection is what? Equal to or not greater. So it's not higher than the ampacity of the conductor. General rule, you with me? That's the general rule. So we're protecting those conductors. In our case, the only thing we're really protecting these service conductors are overload, because we really can't give any short circuit or ground fault protection, because why? It's on the supply side. It's not on the load side. Right now it says a set of fuses shall be considered all the fuses required to protect all the ungrounded conductors of a circuit. A single pole circuit breaker grouped in accordance with 230.71B shall be considered as one protective device. So key thing here for the person that asked the question, we size the conductors based on our loads. We determined whether it was service conductors or service entrance conductors. We follow the rules for sizing. Now we have to have, on those, we have to have at least overcurrent protection. But in our case, we're only going to be able to apply what? Overload protection. Now, the breaker is still going to be overcurrent protection, because, again, that breaker is going to protect downstream faults in short circuits, things like that. But as far as the conductors on the line side, really all we're going to get here is overload protection. So in there, we've got some exceptions to this rule here that says, okay, now the ones we're going to deal with is exception number 5 first. Now, this is an exception that's saying, you know what? You might have an overcurrent device that is providing the overload protection for these service conductors, but it's possibly larger than the rating of the service conductors. And we know that there's an allowance in the code under 310.12 if you're dealing with a service or feeder that is 100 to 400 amperes. It's not over 400 amperes, that supplies 100% of the load on that service or feeder, is supplying equipment like a panel that handles 100% of the load. then I'm able to use what's called the 83% rule, or the reduced conductor size, and it's still considered being protected. Well, if you didn't have exceptions here, then we could not use that allowance, because that rule is saying my conductors can be smaller than what the overload protection would be. And this rule here says you can't do that. However, under exception number 5, it says the overload protection for a 120, 240 volt, 3-wire, single-phase dwelling service shall be permitted. Okay, notice it says service shall be permitted to accommodate with the requirements of 310.12. Again, so this is only going to apply to the service, because again, obviously we're in 230, so we're talking about services. So this is what allows us to have those 83% rule, and it's 83% of the service rating in our case, since we are talking services. Of course, there's a nifty table there as well now that you can just go to that was there years ago. It got removed back to the informative Annex D for examples, and now it's back in the code. Remembering that that table is in a perfect world. It doesn't apply to any adjustment or corrections. It doesn't apply to anything with current carrying conductors that exceed 3. It's a perfect world table. If that applies, then you can just simply size your conductors based on that table and be done with it. Okay. Now, this is the allowance for me to be able to. So the other one that people ask about is exception number 3. Now, exception number 3 is where it says 2 to 6 circuit breakers or sets of fuses shall be permitted as the overcurrent device to provide the overload protection. The sum of the ratings of the circuit breakers or fuses shall be permitted to exceed the ampacity of the service conductors, provided the calculated load does not exceed the ampacity of the service conductors. Okay, so this is that allowance for you to do up to 6 service disconnects grouped in one location. And those service conductors that are coming, let's say, from the point of attachment down to, let's say, a wireway that's breaking off into these 6 different service disconnects that you're permitted to do in 230.71b, permitted to do that, then in this case, if I added up all of the breaker ratings for these services, it probably would exceed the rating of the ampacity of these service conductors, so service entrance conductors, right? But this is saying, no, that's okay. That's fine. As long as you've done a calculation and you know that the calculated load is not going to exceed the amp rating of those service conductors. So this is very commonly used, especially in the grouping, when you wonder, okay, how did they size those conductors that are coming down into, say, a wireway that's maybe branching off and going into 6 disconnects grouped in one location that are permitted by the code, 6 separate enclosures. And you're thinking, how did they, those conductors, is that adequate? Because these breakers add up to way more than that. I mean, let's say I had 6 of them at 200 amps. And that's times 6, that's 1,200 amps of breaker ratings. But what if the calculated load was only 400 amps? Well, then I would size my conductors based on the 400 amps, even though the added up of all the devices would exceed the ampacity value of those conductors. You with me? I mean, I'd be very careful with that, but that is what it's saying. Okay, and that's exception number 3. Okay. Of course, exception number 2, this is the one that says, look, fuses and circuit breakers with a rating or setting that complies with 240.4b or c and 240.6 shall be permitted. So that's a reference. Remember this thing in the code where we say if it doesn't correspond, you go to the next, as long as you follow the rules in 240.4b, 800 amps or less, follow those general rules. If you follow that, then it allows you, for example, to go to the next size, which ultimately means that that overcurrent device, which is providing the overload protection, would be larger than what the conductor's ampacity rating would be, because you're using the next size up rule. If it applies, this is the exception that tells you can do that. So if you ever wondered where that was, okay? All right, so anyway, that's the main ones we want to talk about. So kind of wrapping this up, I gave you everywhere that you need to be in order to size your service. Again, nothing's going to take the place of doing a calculated load. You're going to have to calculate it. But if you're going to be sizing the conductors and you're dealing with overhead service conductors, again, go read the definition, and that's what is applicable to your situation. You're going to be looking at 230.23, and that's size and ampacity. If you're dealing with underground service conductors, you're going to be in 230.31 for sizing. Follow the rules accordingly. Now, once you get to the structure, you're dealing with service entrance conductors. In that scenario, you're going to be sizing based on 230.42, following the rules that we talked about in A1 versus A2, whichever results in the larger conductor, and that's the one you're going to select. And not forget that you have to have overload protection by using overcurrent protection. And since it's on the supply side of the overcurrent protection, it's really only going to give overload protection, but it provides short circuit and ground fault protection on the load side of that overcurrent protected device. Okay? But for us, we're kind of targeting what's on the supply side or the line side of our service disconnecting means. That's where we're dealing with service entrance conductors. That's where we're dealing with underground service conductors or overhead service conductors. Okay? So those are your sizing rules for services under 230. If you have any additional questions, remember what you can do. You can always go to www.paulabernathy.com and submit your questions. Of course, if you want to learn the NEC in detail, you can join our Fast Tracks program. Check out electricalcodeacademy.com.net or .org, and you can find it there as well. But if you have any questions that you want to ask me, please, by all means, submit them. I love answering your questions. Till next time, stay safe. God bless.